Everything's working here, so we'll go ahead and talk about some of these.
Is that working?
It's working.
Oh, it's working.
Recording.
Are we recording?
Recording's on and it looks okay. So let's take a look at some of the bond lengths here. Hydrogen's going to be short because these atoms are small. Hydrogen iodine's going to be kind of long because iodine's big, 161. And so the single bonds we said varied from about 74 picometers to about 300. And so about 100 to 300 picometers of bond length for single bonds. This one, the iodine is going to be, should be the longest bond and the weakest. If we think about it, the fluorine bonds, these are going to be what kind of bonds? sp3 sigmas. We're going to have lone pair, and then here's the bond. And so we expect sp3. The difference between iodine and fluorine would be what? The size. We're hybridizing much larger orbitals. So for iodine, we're going to get this kind of situation. So when we look at the electron cloud density, is it going to be as concentrated? No. And so this should be a weak bond.
Easy to break.
Bond, easy to break.
Is that why we protect iodine?
Yeah, that's why we protect it from light. Now, what you want to look at are some series here. For example, if you look at carbon-carbon single bond, 154, a double bond is 134. Did I draw the double bond already with the PP?
I think so.
Okay. What about a carbon-carbon triple bond? Let's draw that next. A carbon-carbon triple bond is going to be shorter, but when you look at it, how much shorter is it? And so we're going from a single bond at 154 to a triple bond at 120, so it's a little bit shorter. Maybe not as short as you might expect because a triple bond consists of one sigma bond. And so if we look at the sigma bond, what is it? And so when we look at a carbon-carbon triple bond, it looks like this. Let's take an example of acetylene. This is acetylene here with a carbon-carbon triple bond here. And so we have a triple bond which consists of one sigma bond, so one of these lines represents a sigma bond, and the other two lines represent the pi bonds. So we got one sigma and two pi bonds, and that constitutes a triple. And so what we're doing is when we're going from a double to a triple, we're just adding one more pp pi bond. And so this is not going to be, it's significant, but not hugely significant. Now, what is the hybridization of carbon in acetylene? sp3? We don't call it sp3 because we treat the triple bond as one unit, right? And this is one unit. And so we need sp orbitals in a 180 orientation. And so it's going to be sp hybridized. So if it's sp hybridized, then let's go ahead and draw out the orbitals. So we got two sp orbitals, like this. Sp, this is sp. Okay, one of these sps bonds to the hydrogen s. And so this would be just our standard sp sigma bond here. The other sp orbital bonds to what? The carbon over here. We'll have this sp here. And so we'll have an sp sigma bond. So that's a sigma bond here. It's a sp sigma bond. The other sp orbital is going to bond to another hydrogen over here. This is an s. So sps sigma bond there. Okay, now what else is happening? Well, let's take a look at the energy level diagram for carbon. And if we look at it, sp has two orbitals, and that leaves two p orbitals unhybridized. How many electrons does carbon have here? 4. And so how should I fill these? Filling always depends on the Lewis structure. And so 1, 2, what should I do with the third? Pair or promote? Promote it. Third and
How
the
do we
fourth?
determine that again? I forgot.
Because there are no lone pairs on carbon. If there were a lone pair on carbon, I'd pair it. And so we don't know how to fill this until we see the Lewis structure. Once we see the Lewis structure, then we fill it to match the Lewis structure. All right, and so what we have here is we have a hydrogen come in. This is for carbon here. So we'll pick one of the carbons. A hydrogen comes in and bonds here. There. Now, a carbon comes in and bonds to an sp here. And so it's an sp on carbon. So I'm going to write here, sp on carbon is going to come in here on bond. So we get the sp sigma bond there. So what's happening with the p orbitals? Let's take a look. P orbitals. How do I draw the p orbitals in an sp hybridization scheme?
P orbital is in and out of the board.
Yeah, in and out of the board. You want to do that one first? Okay, so we got one p orbital that sticks out and into the board. This is p. And the same thing on this carbon here. Sticks out and sticks in. Okay, we'll label that one this one. And so what we'll have is one electron here. And one electron here. And then even though it looks like they're far apart, we can have overlap above and below the plane. That constitutes one bond, a pp pi bond. So far we have two bonds, the sp-sp sigma bond and a pp pi bond.
The other P orbital is up and down.
Yeah. So let's write that here. So this carbon actually has two orbitals now. One sp orbital bonding, the p orbital bonding here. So that's two bonds. And finally we have another p orbital that's perpendicular to the one we just drew. It's in the plane of the board. Like this. This is the p orbital here. P orbital here. So we're going to get overlap here and here. If I have two overlapping regions, is that a double bond? No, this is not a double bond. This is just one bond because it just so happens they overlap in two regions of space here. And so this is just one pp pi bond. So we got an electron here in this orbital, electron here in this orbital.
How's the two pp bonds look different? One is in perpendicular. How about the other one?
They look exactly the same. If I were to rotate this, this is, let's say, the top view. If I were to rotate this to the side view, it'd look exactly the same. In fact, we could just do that really quick. We'll just draw the side view of this.
What structure is this?
Well, can you?
Linear is the structure. So here's the other pp pi bond. Can I rotate it?
One pp is perpendicular and then one pp is like linear.
Yeah. Look,
Linear as the sigma bond.
no, it's okay. Let me take this. I'm going to rotate it 90 degrees this way. If I take this and rotate it 90 degrees this way, then this is, we'll put the purple bond in the plane and the green bond out of the plane. So let's go ahead and show that here. So now the purple is in the plane. And the green and it comes out and goes in. Plane. It's just a circle. I'm just drawing it wavy like that. It's not wavy like that. And so now the greens, well, the greens are still overlapping above and below. And we have the purples overlapping in the plane. This. You can draw a line to show the overlap. And then the electrons fill in one electron here. How does that look? Do you see it?
I don't know how the green PP bond looks like.
How the green PP bond looks like? Look at the previous drawing. Previous drawing will show you how the green PP bond looks like.
I can't imagine.
You can't imagine it? All right. I'm foregoing the phase. Let me erase this. Okay. Here's the purple p orbital. Here. Like this. And so the purple overlaps here. Okay, so this would be a PP pi bond. This is shown here. This is the upper overlap. This one. It's this one here. This is the lower overlap shown here. And so we have one PP pi bond there. This is the green. They put the green in kind of profile here. And so this one comes out, this one goes in. This one comes out, this one goes in. And so the green overlap like this. You see it? Here and here. And so this would be the green overlap. Would be the second. This is the PP pi bond here. The second one. Can you see it here? The overlapping regions look like this. They twisted a little bit. They twisted a little bit so you could see it kind of in profile. So they twisted the purple over. And so the purple is actually here and here. The purple. And the green is here and here. And so what they're showing is this is more of a volume fill here. And so do you see how the electron clouds are kind of symmetric like this in the cylindrical? See? So you got the electron cloud there. The same thing here. You find kind of this cylinder of electron density around this triple bond in the pi-pi. But that's actually perpendicular. One here, the purple, and perpendicular to that we have the green cigar shape. Is that easy to see or still? All right, so that's a triple bond. The triple bond, because of having a lot more electron density in the internuclear region, it's a pi bond, so the electron density isn't directly in the internuclear axis, but the pi bond is going to help because electrons pull in the nuclei here, and so they're going to pull in the nuclei towards each other and strengthen it. And so the triple bond should be the hardest of the bonds to break. So let's take a look at the bond energies and see that. You see the bond lengths. So the bond lengths didn't change a huge amount, you know. For example, the carbon-carbon single bond was 154, the double bond was 134, the triple bond was 120. If you look at nitrogen, 145 for the single, 123 for the double, 110 for the triple.
The triple bond, like the settling in particular, have anything to do with how volatile it is or unstable?
You know, it's kind of weird because acetylene, you're right, is really unstable, right? Whereas nitrogen is really stable. And so it does relate. You know, the weaker this bond is, the less stable it is. When you look at the acetylene, you know, acetylene should have a carbon-carbon triple bond. Look at the bond energy, 837 kilojoules per mole. If I were just to look at the bond energy alone, I would predict that acetylene is quite stable, you know, looking at it. But then the situation with acetylene is electron rich, and it turns out it's a pretty good fuel. Whereas nitrogen, you know, nitrogen is just N2. Nitrogen's zero oxidation state, whereas this isn't, you know, the oxidation state. But still, yeah, acetylene is highly flammable. You know, they use in welding torches, acetylene. But bond energy, you would expect like an inverse relationship. The stronger the bond, the more stable, you know, versus this.
Are those numbers from experimental data or
Where are these numbers from?
experiments, right?
Yeah, experiments, but these numbers are from average, you know, they're from a whole bunch of different compounds, experimental data. And in fact, these numbers are just average bond energy. The bond energies vary. In fact, this is what this figure shows here. If we look at the here, it really isn't going to vary. You only have one bond. And so this is the average of one experimental reading. Well, 435, 436 kilojoules per mole. But if you look at the hydrogen-oxygen bond energy, take a look at what it is. 498.7, about 500 kilojoules per mole. That's to break off the first. But to break off the next one turns out to be easier. It's less stable here. It turns out to be only 428. And so in this case, the hydrogen-oxygen bond's 500. In this case, it's 428. And so that's a big spread, isn't it, in bond energies for the hydrogen-oxygen. And so what you do is you look at a whole bunch of them, hydrogen-oxygen bonds in different molecules, and then you average them. And so the average hydrogen-oxygen bond comes out to 464. But it could be, you know, in water it was 500. And so when you have an average like this, what else do you want? If you're given an average, you want to know what?
Just the extreme.
You want to know the spread, right? And you want to know how many samples, right? Is it just one sample or thousands and thousands of samples? You know, thousands of different molecules, right? And so, you know, average like this is very tricky to use, isn't it? You're given an average like this, but how do you know? You know, do you have any indication what the spread is? No. And so that's why we have, whenever we show an average, we need to show more information because we need to show what? The 95. We want to capture 95% of the samples within the range, right? That kind of thing. You know, if we took an infinite number of samples. Well, anyway, so look at 464, but you know, it was a bit higher for water, wasn't it? The first one, at least. Well, let's take a look at the bond energies here. For single bond, 347. For double bond, did it double? Almost, but not quite. For triple bond, did it triple? No. It's when you're adding these, you know, pi bond here, it's not really going to double. If it were maybe another sigma bond, like 2 sigma bonds, then yeah, you'd expect it to be quite a bit stronger. But
So
you can't. You know, whenever we have a double, it's always going to consist of a sigma and a pi. And so 837, that's pretty high, let me tell you. Over here, 946. So nitrogen is a very strong bond, almost 1,000 kilojoules per mole. What did I say about nitrogen last time? pseudo-inert gas. It's very unreactive, okay? And because of the high bond energy. But you know, when we talk about reactivity, we got to look at initially how hard is it to break that bond, and then we got to look at how stable the products are.
Why would the nitrogen bond energy like more than double and more than triple?
What's that?
The nitrogen bond energy, like to go to double bond is more than double.
Oh, more than double? That's an interesting point there. For nitrogen, actually, that I don't know exactly why more than double. But usually when you see stuff like this, you know, sometimes size plays a role in it. So, for example, you know, oxygen single bonds like this have unusual characteristics. And the same thing happens with nitrogen, most likely. And have you heard of an oxygen-oxygen bond? It's called a single bond like this is called a peroxide bond. And one of the properties of peroxides is that they're all unstable. And the reason they're unstable is because of this. It's the you know, you'd expect it to be stable because it's small atoms. Small atoms should form strong bonds, right? But it was determined that the reason this bond is so unstable, 142 kilojoules per mole isn't much energy. You know, peroxide bonds are light sensitive, and so if you have a hydrogen peroxide solution, you have to protect it from light, otherwise it'll decompose, it'll break that bond. But the reason why peroxide bond is thought to be so unstable is because the atoms are so small that when they bond, it's good that they're close to each other, but what happens is, as the atoms get closer and closer, what can happen? The nuclei can see each other more and more. And so as you bring the atoms closer and closer, the nuclei start to repel each other. And so it's not, the reasoning that the peroxide bond is so weak is because of nuclear repulsions. The positive charge in one nuclei repelling the positive charge in another nucleus, making the oxygen-oxygen bonds exceptionally unstable. And so this means when you do Lewis structures, you always try to avoid making oxygen-oxygen single bonds like this, because those are typically unstable. Okay, now knowing that, you know, what can you say about nitrogen? It's not the nitrogen-nitrogen double bond that's exceptionally stable. Look at the carbon-carbon double bond, 611. The question should be not why is this more than double. The question should be why is the nitrogen-nitrogen bond so weak? Then that makes sense. Why is the nitrogen-nitrogen bond so weak? What do you think?
Would it be the same?
Yeah, it's likely it's the same argument as with oxygen, because nitrogen and oxygen are right next to each other, and so I think this bond is, you know, look at this, 163 kilojoules means you have to protect this from light also. You know, it's too weak. You know, did we do the calculation for visible light? All right, so if we look at 390 nanometers, 390 nanometers turned out to be 307 kilojoules per mole, roughly. Was that about right? Yeah. 760 nanometer light.
It's like 157.
Is it 157 kilojoules per mole? And so that means, you know, red light is enough to break this. In fact, all colors of visible light are enough to break this nitrogen-nitrogen single bond, meaning this is exceptionally weak. And it's probably due to the nuclei are getting too close to each other, nuclear repulsions. That so goes the argument for this. So are we okay with the double bonds and the triple bonds and the visualizing those? Okay, now I'd like you to do this. I'd like you to, draw the Lewis structure for O2. Oxygen-oxygen double bond, no problem. That's no problem.
For O2?
Yeah. So why don't you just do the same thing? Do the valence bond analysis. Valence bond meaning, overlapping, either unhybridized or hybridized atomic orbitals. Actually, maybe both for O2, and then tell me what you get.